Hi guys, I'm going to look at sketching this inverse trig function. It's sine inverse sine x for all x. It's defined on all real x, of course, because sine x is defined on all real x. The first couple of things to notice is that you know that the period of sine is 2 pi. So we only have to do a 2 pi stretch of it and it'll just repeat from there. The inverse function, I've drawn that just here. So that's sine inverse between -1 and 1. That's the domain, and its range is minus pi to pi on 2 to pi on 2. And the next thing to notice is that the inverse, because it's an inverse function, they cancel each other out, right? Sine and sine inverse will cancel each other out as long as you're on the correct domain. So as long as it's, for example, here we go, if sine inverse of sine of x, that will equal x, provided x is between minus pi on 2 and pi on 2. Yes? So that means that this function here, we already know what that looks like. That's equal to x, for x between minus pi on 2 and pi on 2. So in other words, we've already drawn half the curve. I'll put an axis down here, you can see that. Minus pi on 2 and pi on 2. So we know that it looks like y equals x in here. Done deal. And then we could, of course, draw the other bits if it's got period 2 pi, right? So that if you add, let's add some other numbers here. My OneNote's giving me a bit of trouble here. So it's 3 pi on 2, and that's 2 pi. So we only have to draw it for another section here, and then the rest is repeated. So for example, up here, that's 5 pi on 2. I already know the next bit there because it's periodic. So all those bits are known. Now I just want to focus on what happens in between pi on 2 and 3 pi on 2. So let's have a look at that. I seem to be having a little trouble with my OneNote. Let me just check that. There it goes. All right. So what happens between pi on 2 and 3 pi on 2? So let's investigate that. Let's extend that a little bit out here. Just a little trouble with that. Okay, there we go. Now, when x is in between pi on 2 and 3 pi on 2, let's subtract pi from that, x minus pi. Well, what do you know? X minus pi, and also therefore pi minus x, we'll need that a little bit later, are both between pi on 2 and minus pi on 2. That's going to help us later. We can actually use that property of the inverse function that we used up here. We can use that again. And we need a little trick. And here's the trick. You just write sine inverse sine x equals, the trick is, you've got an x, you minus pi, and you plus pi. Tricky, hey? And you put them into two groups. Don't forget now, just to recall, sine alpha plus beta equals sine alpha cos beta plus sine beta cos alpha. We're just going to need that one for a tick. And we'll put a big thing on that. So that's going to be sine x minus pi cos pi plus sine pi, which is 0, of course, cos x minus pi. So that one's 0 because sine pi is 0. Cos pi is actually -1. So that's going to give us sine inverse sine. Well, it's really minus sine, right? Sine is odd function though. So we can actually pull that minus sign inside the sign, becomes pi minus x. However, pi minus x is between minus pi on 2 and pi on 2, so we can just let that equal pi minus x. So therefore, y is equal to pi, I'll just write y up here too, minus x, when x is between pi on 2 and 3 pi on 2. And in particular, when x is equal to pi on 2, let's work out the y value. Y is equal to pi minus pi on 2, which is pi on 2. So that's up here. And when x is 3 pi on 2, that's the other end of it. Y is equal to pi minus 3 pi on 2, which is minus pi on 2, which is that point right there. You're going to join those two right there, and there you have it. And the rest, you just infer. So I guess we shouldn't have drawn that one in. We'll put the inferences in blue. So we can just now infer that that goes like that, this one goes like that, and it keeps on going. It's a big zigzag job. Now that really wasn't that hard, was it? Of course, you can continue that and generalize. You can now say, okay, what about when x is in between 3 pi on 2 and 5 pi on 2, and so forth and so on. There's quite a nice little calculation, which I won't do it unless someone requests it. But can I just show you the formula? In general, for fun, the actual equation of this is actually equal to, so this is sine inverse sine x, but it's actually equal to, I've written it down somewhere, there it is, it's minus 1 to the power of n, x minus pi n, and that's for x between minus pi on 2 plus pi n, multiples of pi, in other words, n is a whole number, and pi on 2 plus pi n, where n is an integer. Yeah. So you could put in n equals 0, n equals 1. So for example, let's do the little case here. For n equals 0, that's our easy case. Y is equal to minus 1 to the 0, x minus 0 times pi. So that's just x. We knew that, y equals x. For n equals 1, that's the one we just did above. That's going to be minus 1 to the power of 1, x minus pi times 1. So that's equal to pi minus x, exactly as we explained at the top here. And it's a lovely pattern after that. It just keeps zigzagging, pardon that. Minus 1 squared, then it's going to be x minus 2 pi, which is x minus 2 pi, right? So can you see the pattern? The next one's clearly going to be 3 pi minus x. There's an obvious pattern there, so you can, I thought that was quite nice. I thought I'd share that with you. I hope you appreciate that. If it's too much, no one's ever going to ask that in an exam, right? But that's just interesting. And it'd be a nice little derivation for you to work that one out, assuming this is the domain here. Use the same trick that I used above. You know, that trick up here, this trick here, use that on that. And it'll flow. Then use that formula, sine alpha plus beta. Well, I think I'll leave it there. I'll put an image of that on my blog as well, which I'll put in the link for you. And other than that, thank you for listening, and I'll see you guys next time. And yeah, bye.